Dr. Vanden Bossche, the floor is yours.
Okay, thanks, Jean-Pierre. So seems like we are now gonna take a deeper dive in, well, the vaccination topic, which is, of course, a topic that is heavily debated nowadays. And Jean-Pierre put this slide as a kind of introduction of my session, because I guess what I am very worried about, and I have been making this call since quite some time, is that mass vaccination will inevitably drive immune escape, will force the virus to escape the immune response that is actually induced by those vaccines. And of course, I will come to this in a moment. I will explain this, but I think the slide that of the publication is just illustrating that basically this has already been documented in the literature for viral diseases, that if you massively, and this was in animals, vaccinate animals with a vaccine that prevents against disease, but not against infection, that this is basically forcing the virus to select mutations that enhance its infectiousness. So next slide, please. Yeah, well, we can skip this slide. This slide, yeah, I will explain the abbreviations as we go. So first thing I wanted maybe to draw your attention to is that, well, we are dealing indeed with a pandemic, but we are no longer dealing with, I would say, the natural course of a pandemic. So the natural course of a pandemic, and a very nice example, is the influenza pandemic back in World War I. And there we had an influenza pandemic, which was not, I would say, influenced by any human intervention. And what do I mean by human intervention? Well, the kind of human intervention that we are now implementing on a massive scale is, first of all, the mass infection prevention measures, wearing masks and physical distancing and disinfecting, washing hands, etc., on a global scale. And second, the mass vaccination is, of course, also large-scale human intervention. None of this existed during the war, the First World War, and so we could witness the natural course, actually, of a pandemic. And this is very, very important to understand, because, yeah, I would say this is a pretty complex interaction between the virus and the immune system. And if you don't understand this phenomenon, if you don't understand the natural course of a pandemic, then I think you have no right whatsoever to intervene in that course, hoping that you will shift this into a kind of course that will be more beneficial for humankind. And I will show you that it is exactly the opposite what we are doing right now. But let me first explain on these slides. And I was saying no human intervention. People were not wearing masks, you know, when in World War I, and there was not these recommendations on physical distancing or any kind of infection prevention measures. At least not measures that you know, had a large impact. And there was certainly also no mass vaccination. So what do we see? And I will try to explain this in as simple words as possible. The first wave is, of course, easy to understand. The virus is new to the population. Okay, nobody has antibodies, right? So, but some people, and actually a large part of the population, has a strong innate immunity. And I will come back to this, and I will explain how this works and why it can protect you. But what we all know is that we have witnessed how, for example, elderly people, people with underlying diseases, or that are otherwise immune compromised, are more vulnerable to getting the disease, right? I mean, this is something which has been very, very obvious as we were confronted with the beginning of this pandemic. So these people get the disease, Some of them, of course, or majority will survive. Some people will die. But then there is an interesting thing. And as I was saying, if you are dealing with a complex thing like a pandemic, and you don't understand all the things that all the observations made, and some things are mysterious, you cannot intervene. You cannot afford to leave any stone unturned in the understanding of a natural pandemic, because the second wave, for example, the second wave of that pandemic was hitting the younger population. The second wave was a severe wave, as you can see, and it was very, very focused on making young people, ill. This was a huge problem in World War I, of course, because basically more soldiers died of influenza in the trenches than they were dying of, wounds or injuries of the war. So how can you explain this? How can you explain that these people, I was just saying, because of their strong innate immunity, were completely protected during the first wave, and then all of a sudden they get massively, this population get massively hit by disease during the second wave. So, and then there is the third wave, and then we see that the pandemic is transitioning into what we call an endemic phase, where you can have some flare-ups, but where basically you get what we, a notion that we are all very well aware of, and which should be the ultimate goal also of the vaccination, which is herd immunity. So let me explain how that works. So the fact that we have essentially the second wave hitting younger people. But before we get to this, we should first have an understanding, again, a phenomenon that is not well understood, and every second publication starts with, COVID remains a little bit mysterious. We have still not a deep insight in the pathophysiology and the immunopathology of this virus. And so there is a need clearly to understand this, to understand better what is going on. But again, how can you proceed with immune interventions if you don't even understand how the virus is exactly interacting with the immune system? Where is the science that enables us, that allows us to intervene when we don't understand this? So what is happening, as you can see on this slide, is, and again, I'll do my best to explain this in very simple words, is the virus comes in at the upper respiratory tract, and there you have cells, epithelial cells of the upper respiratory tract that are susceptible to the virus. And then the virus can enter into those cells by docking on a receptor. And so once the virus gets into the cell, it can start to replicate, will destroy the cell, the virus will be released. And when the virus further propagates to the lower respiratory tract, for example, and to the lungs, and there you can get more severe disease. And we all know that that is the place, or that is at that point in time, you may get these cytokine storms and heavy inflammatory symptoms where people basically need to be hospitalized. But there is another interesting phenomenon. And I mean, if there is one thing in the whole COVID pandemic and in the understanding of the pathogenesis of the disease that has completely been neglected, then it is the situation and the cycle of the virus in people that don't get symptoms. So why are people getting symptoms, others are not getting symptoms? I was saying, well, it's innate immunity, yes, but how does that work? How does that work, and how can you basically explain that the vast majority of the population, and these are not just youngsters, I mean, even some elderly can be perfectly protected by their innate immunity. And we don't understand exactly how that is working. And that is a major shortcoming, because the arm of the immune system that has been completely neglected in the whole consideration of how this pandemic spreads amongst the population, it's the innate immunity. So we have the immune system has two arms: the innate immune system and the acquired immune system. So the acquired immune system, these are the specific antibodies that the body will build once you have gotten the disease. You build antigen-specific antibodies, and those will protect you. But you have the other arm, which is the innate immune response. And this immune response is not, we call this antigen specific, I could say, is not variant specific. It is not even corona specific. So it can cover a large amount of different viruses, for example, certainly all coronaviruses, certainly all variants of COVID. And how does that work? Well, it works through what we call natural antibodies. So the natural antibodies are already present at birth. Especially children have a strong reservoir, I would say, of natural antibodies. These natural antibodies are secreted by certain immune cells that are very well presented in the young immune system. So these natural antibodies, what do? Well, the natural antibodies, they can complex with the virus. So they can recognize the virus. They can build a complex with the virus, as you can see here. And then this complex is, in fact, internalized into what we call antigen-presenting cells. What is an antigen-presenting cell? Well, let's keep things very simple. An antigen-presenting cell is a cell of the immune system that is going to internalize a foreign body, for example, a virus, and that is going to digest that virus and then present the pieces of that virus on its surface. Yeah, you see the small bullets here on the surface of the antigen-presenting cell. And that is basically required in order for the immune system to well recognize the pathogen. So the pathogen is cut apart in pieces, presented on the surface of those cells, and then can be recognized by the immune system. But what is very interesting with COVID is that in asymptomatically infected people, so people who get infected but who don't develop the disease, these patterns on the surface of the antigen-presenting cell are recognized by natural killer cells. So natural killer cells are innate immune cells, part of the innate immune system, that have the capability of recognizing molecular patterns that are extremely conserved. A complicated word for scientists would be phylogenetically conserved patterns on the surface, for example, of antigen-presenting cells. And so these natural killer cells do not recognize, in contrast to, for example, the typical antibodies, also generated by vaccines or after natural infection. Those antibodies, they recognize a specific part of the virus, for example, the spike protein. The NK cells, the natural killer cells, they do not do this. They recognize molecular patterns that are shared amongst several different variants. So when you have an antigen-specific antibody, as I was saying, induced by natural infection or, for example, by vaccination, this antibody will recognize a very specific part of the virus, for example, the spike protein. And now when we have a lot of variants that have a different constellation of the spike protein, well, then these antibodies will no longer recognize them or will only partially recognize them. I mean, the NK cells, they don't care. The natural antibodies, they don't care, because what they recognize is a molecular pattern on the surface of the virus, and that molecular pattern is shared amongst several different variants of COVID, and is even shared amongst all coronaviruses. So now what happens? So the NK cell gets activated, and at a very early stage of infection, these patterns are also expressed on the surface of the epithelial cells, the cells that are susceptible. So what's the problem? Well, there is no problem. The virus infects the cell, as I was saying. It enters into the cell, and immediately, at a very early stage of infection, these patterns are presented on the epithelial cells, and the NK cells, they have been mobilized, they have been sensitized, in fact, to recognize those patterns, and they immediately kill the infected epithelial cell. So that is the reason why asymptomatically infected people will be infected, may spread the virus for maybe a week. I mean, definitely the concentration of the virus shed is certainly not as high as in people who do get a disease, and it's certainly very short-lived, because the virus get eliminated after a few days, maybe a week. So the infection gets completely abrogated. This virus gets kicked out, and the asymptomatically infected person is completely free of virus, right? That is a different situation, of course, than when you don't have these antibodies, or when these antibodies are only present in low quantities, or people who are not in good health. I mean, that is documented in the scientific literature, and I posted a lot of scientific literature, on the website that is going live today, and also on LinkedIn, etc. It is proven that people who are not in good health have poor natural antibody production. And so they cannot drive the virus into this killing pathway. So the virus is going this way, where it ultimately will cause severe disease. Because severe disease is the most interesting situation for the virus. Why? Well, I was just saying, in asymptomatically infected people, the virus is just, shed for a very short time in relatively low concentration. Whereas if you get a disease, my goodness, I mean, you are shedding virus for several weeks, and also at very high concentration. So I guess we can pass on to the next slide. Yeah. So this is the only thing that is a little bit complicated, but it is so important to understand this. What happens is that, and don't look maybe at the slide right now, just please listen to what I'm telling you. When people that are asymptomatically infected will clear the virus, what we see is that all of a sudden we see a surge in antibodies. A surge in antibodies that is not extremely high. Certainly the antibody levels are not as high as in people who get symptomatically infected. And the surge is also short-lived. So what does that mean? Well, it means that after infection get cleared, people develop their antibodies, but in 6 to 8 weeks, these antibodies are no longer detectable. So again, you could say, well, okay, that is an interesting observation. But I was like asking myself, how does that come? What is the purpose of this? Because these antibodies don't play any role in eliminating the virus. I was just saying the NK cells, the natural killer cells, take care of this. And on top, these antibodies come at a point in time where, in fact, the virus has already been eliminated. So it can't be that these antibodies are responsible for eliminating the virus. So what is their role? Again, if you think that during thousands and millions of years, sometimes, of evolution, and coronaviruses being established in all kinds of mammalian and vertebrate populations, this would be a phenomenon that is just there and doesn't make sense. You're completely wrong. Because if it wouldn't make sense, if it wouldn't have any significance, then evolution would not conserve this type of things. So this is the point where I'm saying, if you study this and you don't understand what this means, then stop it, or you do your homework and try to find out what is going on here. Because one thing is certain, because this phenomenon got conserved throughout evolution, throughout the co-evolution of the pathogen with the immune system, it is important. And so you better find out what is the meaning thereof. So what is the meaning? Well, and still don't look at the slide. You have to realize that antibodies that are specific, because these antibodies are specific for the spike protein, they have always a higher affinity. I hope people can understand the word affinity. They have a higher affinity for the spike protein than the natural antibodies. I was just saying the natural antibodies, they recognize the virus as one entity. The antigen-specific antibodies induced by natural infection or by vaccination, they specifically recognize spike protein, so they have a high affinity for the spike protein. So now when it comes to binding to the spike protein, of course, the specific antibodies will always have a higher affinity than the natural antibodies. And now we are going to look at the slides. So what I'm saying is these are the specific antibodies, again, induced by natural infection or, for example, also by vaccination, if you use the spike protein in your vaccine, which is the case with the current vaccines. So this antigen-specific antibody is going to bind, for example, very strongly to the original virus. What do I mean with the original viral strain? Well, this was the kind of strain that was initially responsible for the pandemic at the very beginning. And this, the spike protein of this original virus is exactly the spike protein that is in the vaccine, for example. Or if you get infected by this virus, you will build antibodies, and they will have a high affinity for the virus, for the original virus. But if now you have a variant, variants mean there are changes in the spike protein. So the spike protein, it doesn't look any longer exactly the same as the spike protein on the original virus. And as I was saying, because these antibodies are very specific, well, these antibodies can no longer recognize these variants as well as they recognize the original virus. But nevertheless, they still have a relatively high affinity for this virus because they are still directed to the S protein. They're still specific. And even though they have, for example, lower affinity to the variants than to the original virus, they will still be able to outcompete the natural antibodies for binding to the very same virus. So what is important to notice here on this slide is that the natural antibodies, and this is key, they have a broad binding capacity. They can bind, I already mentioned this previously, they can bind as well, without any difference, to the original virus as to the variants. Because as I was saying, they are recognizing patterns on the surface of those viruses, and those patterns, these molecular patterns, are conserved. So their binding strength to those guys is identical. But their binding strength is always lower than for the spike protein. Their binding strength for the spike protein is always lower than antibodies that are specifically directed against the spike protein, no matter whether they are directed against the original spike protein or the spike protein of the variants. So what does that mean? Why am I saying that those antibodies are outcompeting natural antibodies for binding to spike protein? Because the spike protein is so important. It is the spike protein that is responsible for interacting with the receptor. So it is the spike protein, in other words, that is responsible for the infectiousness of the virus. So variants have a higher binding strength to the receptor than the original virus has. Hence, why these variants have higher infectiousness. So what counts in terms of antibodies is always the binding strength to the spike protein, because that matters in terms of infectivity, infectiousness of the virus. So if you have natural antibodies, if you have specific antibodies, they will, in terms of binding to the spike protein, outcompete the natural antibodies. So I was just saying the natural antibodies are the guys that enable protection against all those variants. So now we are going to recapitulate a little bit, because I was talking about the waves in a natural course of the pandemic. We're still talking about natural course of the pandemic. The second wave, okay? The second wave, the young people that had good innate immunity. What happens? They got infected with the virus during the first wave. No problem. They didn't get a disease, but they started to develop, of course, a short-lived surge in antibodies with relatively low affinity, short-lived, not high concentrations. So normally that doesn't matter. That doesn't, that is not a problem, unless at that very moment where they have this short-lived surge in antibodies, they get reinfected. Because if they get reinfected at that very moment where they have these short-lived antibodies, they will be facing a suppression of their natural antibodies. The natural antibodies will be outcompeted. They're bypassed. And when this natural immunity is going to disappear, these youngsters become susceptible, because they cannot rely on these antibodies, certainly not if there are variants, because I was just saying they have low affinity. They will still bind to the spike protein, but this binding to the spike protein will not, because it's so weak, it will not prevent these variants for binding to the receptor on the susceptible cells. And that is because this binding is very, very strong. I was just saying these guys are highly infectious. They have changed their S protein in a way that they can bind much stronger to the epithelial cells. So what happens is, okay, during the first wave, people get infected, infection is spreading, the infectivity rate in the population is increasing. So you get more and more virus in the population. So, and this is important, the likelihood that somebody who happens to have this short-lived raise in antibodies gets reinfected at that very moment becomes higher and higher. So the likelihood that somebody gets a suppression of its innate immune response becomes higher and higher as the infectivity in the population spreads and increases. So with increasing infectivity in the population, the likelihood that young people who had a good innate immunity and because of that reason were protected during the first wave are facing momentarily, at a very moment of the reinfection, a surge in their antibodies becomes increasingly likely, and hence it becomes increasingly likely that they get reinfected at the very moment where their innate immune system gets suppressed, because the natural antibodies are outcompeted. And that is the reason why all of a sudden the virus can shift, or the wave of disease and death can shift to the youngsters, to the young people, without any need for the virus to increase, in fact, its infectiousness. Because, when the virus infects them and they have this suppression, well, the virus, can simply infect them and make them ill. So now what happens? Okay, these people get ill, And maybe we should shift to the next slide. I think we have this thing with the reservoir. Yeah, that's exactly what I'm saying. So yes, I need to explain what are NACs and non-NACs. Well, it's very simple. So the NACs, these are people that have natural asymptomatic carriers. So very easy. These are the people who during the first wave are naturally protected against the disease, asymptomatically infected. And the non-NACs are all the rest. These are the people who are during the first wave who are vulnerable because they have low innate immunity. So first wave, people get the disease, and there is less and less people available, I would say, who can get the disease. No problem, because in the meantime, the likelihood increases that people who got asymptomatically infected during the first wave are now dealing with this short-lived surge in antibodies whilst they are reinfected by the virus, and hence their susceptibility increases, and so the virus can jump. Well, it's not the virus, it's the wave, in fact, of disease that jumps, in fact, now to the younger people. So again, what happens here is that it's of course not all the young people. It will be, first of all, people who have the lowest innate immunity, because this suppression is never complete. And the suppression will, of course, lower the capability of natural antibodies to intervene. But there will still be a number of people who have still sufficient natural antibodies to protect them against all, different variants or against the COVID virus. So this reservoir, I would say, of young people who could potentially be getting the disease decreases as the virus spreads in that population. Is that a problem? Normally, it's not a problem, because when that happens and the virus is like, okay, it's becoming increasingly difficult to get these people ill, to make them ill, because the remainder is still having very, very good innate immunity. And, the virus is looking, how can I move to another population? And yes, for sure, it can, because now in the meantime, the guys that got infected during the first wave, they have declining antibody titers, right? And they become susceptible again. So again, the virus can, without any problem, just go back to that population. In the meantime, there is certainly also partial part of that population that have their innate immunity diminished. So it can infect again its people. But what happens here is that these people, a large part of these people have already seen the virus, right? So they can immediately reactivate their immune system, because we call this immunological memory. Antigen-specific antibodies, the spike-specific antibodies, they have immunological memory. So once they have seen, when they have seen the virus and they see it again, like half a year later or even a year later, they can immediately bombard the virus with a huge raise and concentration in antibodies. So more and more, the virus will infect for a second time. People who have seen the virus will immediately come up with a huge concentration of antibodies that will, of course, diminish the spread of the virus. And that is how we ultimately get to this kind of herd immunity. So that is important to understand, because the question now is, what happens if we have, for example, in this stage, and frankly speaking, that is exactly what, at least in Europe, we are seeing right now. We are seeing that a lot of young people now get infected. More and more youngsters get to the hospital, get severe disease, because that is the place where the virus is now causing disease and death. We are having young people, children, who were perfectly healthy, who are now on mechanical ventilation, right? And they had no underlying disease, but they had suppression of their innate immunity because of the short-lived antibodies that they had. And during that time, they were reinfected with the virus. So this is important, I would say, to understand, because if you now consider that we are massively implementing infection prevention measures, we are, of course, giving the virus a very difficult time. We have been implementing these prevention measures already, a long time ago, over a year ago, and we saw these highly infectious strains popping up the end of last year, November. So this was definitely way before the mass vaccination got implemented. So I can tell you, if you look at pandemics that have been documented, and this raised my attention, of course, in the first place. We have never seen that all of a sudden highly infectious strains pop up, not one, not two, a whole series of them. And you can have mutations all over the place and, all kinds of variations. But now that all of a sudden, the variants show mutations or have selected mutations that all converge to that S protein that is responsible for their infectiousness, I thought, well, that cannot be a coincidence. And I immediately connected this with the fact that, okay, what have we been doing? We have exactly trying to prevent the infectivity of the virus. So the virus, what is the virus? The virus is going, to select mutations in the spike protein that enable it to counter this effect of infection prevention. And that is how we see all these mutations in very particular domains in the S protein that are responsible for enhanced binding to the receptor. And who says enhanced binding to the receptor says automatically enhanced infectivity. So there is something that people, disagree with me. But again, I'm challenging them to have a scientific debate. Because, and Jean-Pierre, could we go back to the previous slide? Because this is important, I think. The one with the, this one. So now, when does a virus escape, and how does the virus escape? And what is, the virus is escaping in a very targeted way. We call this selective immune escape. It is very selective. It's concentrating itself on changing or modulating the S protein to enhance infectivity. And how can it do it? Well, there is, I would say, almost a law in vaccinology or immunology. In every textbook you can read this, and it's according almost to the laws of Darwin. If you put a living organism, and especially a living organism that has a high capacity for mutation, if you put such a living organism under infectious pressure, immunological pressure, for example, by mounting antibodies, you put it under pressure, but at the same time, you still leave a little bit the door open for that organism to replicate, well, then for sure, that organism is going to select mutations that enable it to overcome the pressure that you are putting. Frankly speaking, this is all the same mechanism for, antimicrobials. So in that way, you put pressure, you leave the door open, the virus say, oh, you're giving me a tough time. I'm going to select mutations that will enable me to overcome this. And selecting mutations is not a problem because there are mutations all over the place. So what does that mean? Where do we have, at what point do we have such a situation where there is immune pressure that is not optimal because it leaves the door open for the virus to replicate? Well, it is exactly at that stage where I was saying that people who got asymptomatically infected during the first wave have a surge in antibodies, a surge of antibodies that are not fully mature, that are only short-lived, that don't reach very, very high titers, that are not responsible for elimination of the virus, because I told you these are the NK cells. This is a suboptimal immune response. When the virus gets in again, you have all the conditions for immune escape, namely a suboptimal immune response that gets confronted with an infection with a virus. So the virus is able to escape that immune response because it is suboptimal. And what it will do is that it will now try to modify its spike protein in a way that it binds much stronger to the receptor of the epithelial cell because in that way, by doing this and by binding stronger to the receptor than in fact it binds to the antibody, it is able to in fact outcompete the antibody. And so that is a typical place in asymptomatic carriers where the virus is able to escape the immune response. It will not normally do this. I was telling you, during the natural course of the disease, the virus has no need to increase its infectiousness, because by the time that it becomes a little bit difficult for the virus to still find young people that it could potentially infect, and the innate immunity of whom is low enough for the virus to cause disease, by that very moment, there is already a decline in the antibody titers in the population that got initially infected, and it can just go to those and cause disease in those people, because that reservoir will again be much larger than the reservoir that is still available in the young population. So first of all, the infectious strains that we are seeing right now are the consequence really of immune escape by an opportunity that is generated for the virus in asymptomatic people. So what is the next problem? And I mean, I'm telling a lot of things, but frankly, I'm coming to the end of my presentation almost, because there is only one thing left we need to talk about, and it's mass vaccination. Well, remember, during the natural course of a pandemic, I was saying the third wave is caused by the fact that people become again susceptible, and that the virus can again go back from the people who used to have a good innate immunity to people who became seropositive after the first wave. So, but what happens if you now prevent those people who were infected and got the disease during the first wave, if you prevent them from having declining antibody titers? What happens, in other words, if you immunize these people, like we have been doing at least in a lot of European countries? We have started with immunizing the vulnerable people. So these people, due to vaccination, have now long-lived antibody titers, and the virus just cannot get in because they are to some extent protected. And they are protected maybe, and we know this, against the variant strains. We know that shedding is taking place, and that the vaccines cannot prevent these highly infectious strains from being shed. But that is not the most interesting scenario for the virus. As I was saying, for the virus, in order to ensure its perpetuation, it is critical that it can make these people ill. Because if you make the people ill, being a virus, you will ensure very strong and a long-lived viral shedding. And that is needed, frankly speaking, for the virus to continue, or to ensure its perpetuation. Now, if you prevent this, and to some extent we are still preventing it, just quite recently, as Jean-Pierre showed, that we have now even some strains where we have only like 20-30% of efficacy against disease. But so far, we still had some protection against the disease. And so the virus was not really, doing very much in terms of ensuring its perpetuation in the vaccinated people. So then it has no choice, but it has to stay with the younger people. But there the reservoir got almost exhausted of people that potentially could get a disease. So what is it going to do? It is going to increase its infectiousness, because when it increases its infectiousness, and I was saying the condition is there because these people are now, with increasing infection rate, increasingly exposed to reinfection with the virus while they're having suboptimal antibody titers, and so the virus can escape. And the virus will increase its infectiousness, and by increasing its infectiousness, I mean, people, will become more susceptible. So their natural antibodies get suppressed. That is during natural infection. But now, by increasing its infectiousness, it can make these people much more susceptible. So it will take a bigger part of the younger population just by increasing its infectiousness. And that is what we are seeing right now. The virus has to stay with the younger people, and you know, the wave of disease in the younger people must increase in order for the virus to ensure its perpetuation. And so that is where the vaccination is starting to have dramatic effects, and people say, well, you know, no. And the reaction is, of course, oh, wow, these vaccines protect elderly people. Look, I mean, there is less hospitalization, there's fewer hospitalizations, they don't get severe disease. So what we need to do is to vaccinate the younger people. I mean, this is just going to be a catastrophe, because we see already that the virus is escaping all the time to the antibody responses. So frankly speaking, it's just a matter of days or weeks till we have full resistance. Yes, resistance against those vaccines, also in terms of protecting against disease. And what's happening then is that folks who got vaccinated, you know, they can simply throw their antibodies in the bin, their vaccinal antibodies, but they also have they can no longer rely on their innate immunity. Why is this? Well, I told you previously that despite the fact that these antibodies will no longer prevent the virus from interacting with the receptor on the cell, their binding will still be strong enough to the spike protein to outcompete the natural antibodies. So you're left with nothing. If you would not get the vaccine, or you would not have these antibodies, you would still be able to rely on the only ally that is left, which is your innate immunity. And so I think this is really the core of my message, that antigen-specific antibodies, they can be detrimental, especially in people who are in good health. Because people who are in good health, they can rely on their innate immunity, provided they get regularly exposed. Why I'm saying this? Because the innate immunity has no memory. It's like you're sitting on your chair for like 3 weeks, your muscles are gonna wane, you know, I mean, it is the same with the innate immune response. Your innate immunity, if it's not trained, if you don't go out, if you're not exposed, if you lock in young people, etc., their innate immune system will not be trained. But if you're in good health and you train this, you will have a strong innate immunity. What is the advantage? For God's sake, innate immunity protects against all variants, against all coronavirus. So it is incredibly precious. So you cannot put this at stake. It's just impossible. So Jean-Pierre, I think we can. Well, the rest of the slides will be very, very fast, because prophylactic vaccines or for use in conventional. Yeah, well, this is the other thing I'm saying, of course. So what is happening right now? What is happening right now is, I told you, we are in a war, and do we know our enemy? Well, I was just saying we don't even understand the pathophysiology or the immune pathology of the virus. That is our enemy. We don't understand. We don't know our enemy, in other words. We don't understand the natural course of a pandemic. So we don't understand what is the strategy of this war, what is going on in this war. And then we come with a weapon that we don't use properly. Why I'm saying this? Well, all of the vaccines that are right now, not in the pipeline, but are already rolled out, are prophylactic vaccines. What do I mean with prophylactic vaccine? A prophylactic vaccine is typically a vaccine that you should not use while the individual is exposed to a huge infectious pressure. We are in the midst of the pandemic, guys. So that means that if you are vaccinating somebody while this person is at risk of being exposed to the virus, you get a huge problem. First of all, you may not be able to protect that person, because before you have the full-fledged developed immune response, this person may already be infected, and hence, you can no longer protect them. Secondly, imagine you vaccinate somebody who is at risk of being exposed. He may already, or she may already be incubating the disease. And then you come with a vaccine. well, very often, especially with live vaccines, which is not the case here, that is not doing very good to the patient. But the third thing is, when you vaccinate somebody in the midst of a pandemic, whilst being exposed to the virus, you are having a high likelihood that this person, while developing this immune response, is going to face the pathogen, and hence the pathogen will be confronted with a suboptimal immune response. That is happening with all the people who got, for example, their first dose, and then, wow, they just go back into the pandemic, guys, exposed to the virus, etc. Their immune response is not mature yet. So it's suboptimal. So this is really asking for immune escape. So what I'm saying is that we don't know our enemy. We don't understand the strategy in this war. We don't use our weapon, the vaccines, properly. And hence we are sending thousands and millions of people to the front line, in the trenches. And we have no plan B. And I mean, I can tell you, this is the first time in the history of mankind that we humans are intervening in such a massive way, with massive infection prevention measures, with massive vaccination campaigns, where there is plenty of opportunity, as I try to explain you, for the virus to be facing suboptimal immune responses and to escape. And that is why I'm saying, and I'm scientifically convinced of this, that this we are making of a virus that was initially pretty harmless, we are making really a kind of monster of this virus, because the more we chase it, the more it will become infectious. And this is right now already, starts already to be a disaster. And I'm telling people, who are not listening, scientists, top scientists, health authorities, I'm telling them, well, look at those countries who have their successful mass vaccination campaigns implemented, like the UK, like Israel, like Gibraltar, and very soon also the US. You see the declines, of course, you have an effect, but for sure, after this decline, you will see a huge wave of disease and unfortunately also mortalities, despite the fact that these countries are going to further increase their vaccine coverage. So then, when people will see that despite increased vaccine coverage, 60, 70, 80% of population, all we get is increased rates of mortality and morbidity, then people will probably realize, responsibles will probably realize, oh my gosh, something went wrong here. But what do you think? I mean, if you intervene on a large scale in this pandemic, there is only two possible outcomes. Either you have a fantastic effect, or you generate a disaster. And I'm certainly not a drama queen. I mean, this is based, guys, on science. And so I'm glad that Jean-Pierre started the introduction with the slide where, my goodness, guys, this has already been documented, that vaccines that do not protect against infection, that do not prevent the infection, but only the disease, that this is a recipe for immune escape and for breeding variants that have a higher infectiousness.